Next method, Mallows Cp statistics. This is a full model. Y is observational vector of order n cross 1. X is a coefficient matrix of order n cross p plus q. Vector of beta is a vector of regression coefficient of order p plus q. Plus epsilon of order n cross 1. Here, expectation of epsilon is null vector and dispersion of epsilon sigma square in. In is a identity matrix. We partition X as where order of x1 is n cross p, order of x2 is n cross q. Now partition beta vector as beta 1 of order p cross 1 prime beta 2 prime q cross 1, order of beta 2 is q cross 1 whole prime. Suppose we use only p explanatory variables, then our reduced model is y curve x1 beta 1 plus delta. Since this is a regression model, rank of x is p plus q rank of x1 is p rank of x2 is q. Now OLS estimators of beta 1 equal to beta 1 hat x1 prime x1 inverse x1 prime y curl. And y hat equal to x1 beta 1 curl hat is equal to x1 prime x1 inverse x1 prime y curl. We denote this matrix by h1 y curl, and h1 is the idempotent matrix, and rank of h1 equal to p. Now capital gamma P denoted as expected outweighted squared error loss of y hat equal to expectation y hat minus expectation of y hat minus expectation of y prime. Sorry, expectation y minus expectation of y prime, y hat minus expectation of y. This is equal to y hat is nothing but a h1 y curl, expectation of y, this is obtained from full model x beta whole prime h1 y x beta. Here we mention that if we use only p explanatory variables, and if this model, this subset model y equal to x1 beta 1 plus delta is an appropriate model, then this capital gamma P should be small. Now this equal to y curl prime h1 y curl minus y curl prime h1 prime x beta curl minus beta prime curl x prime h1 y curl plus beta curl prime x prime x beta curl. Here we use the fact that H1 is a idempotent matrix, then you can get this expression. Now we write this as expectation of y curl equal to x beta, so this should be beta curl prime x prime h1 prime is a h1 is a symmetric matrix, so h1 prime should be h1 minus beta curl prime x prime h1 x beta curl plus beta curl prime x prime x beta curl. So this is gamma p. Now expectation of y curl h1 y curl equal to expectation trace, since this is a scalar form, so this is same as trace of y curl prime h1 y curl. Now we use the fact trace of AB equal to trace of BA, so this is equal to trace of H1 y curl prime. Now trace of H1 expectation y curl prime, so this is equal to trace of H1 dispersion of y curl, which is equal to sigma square in plus expectation of y curl into expectation of y curl prime. So this is equal to beta x beta, this is equal to x beta curl into x beta curl prime equal to sigma square trace of h1 plus trace of hx beta curl x beta curl prime equal to sigma square trace of h1 plus trace of AB. Since trace of AB equal to trace of BA, so we write it as trace of beta curl prime x prime hx beta curl. So if we put this value in 1, then we get gamma p equal to again I want to mention that this is a scalar form, so trace of this is nothing but a simply this. So now we put this value in 1, then we get gamma p equal to sigma square trace of h1 plus beta curl prime x beta curl plus this minus twice of this. So this is nothing but a minus 2 beta curl prime x prime h1 beta curl and plus this, so this two, so this is nothing but a minus of beta curl prime x prime h1 x beta curl. Since h1 is an idempotent matrix, so trace of h1 is nothing but a rank of h1. Hence rank of h1 is p. Since rank of h1 is p, so trace of h1 is p. So this is p sigma square plus beta curl prime x prime h1 bar x beta curl, where h1 bar equal to I minus h1. We denote this as equation number 2. Now we start with this expression and using similar step we get this. Again, sigma square trace of h1 bar is nothing but a, since h1 bar is a idempotent matrix, so so this is, now replace this value by expectation y curl prime h1 bar y curl equal minus 6 trace of h. gamma p equal to p sigma square plus expectation y curl prime h1 bar y curl minus sigma square trace of h1 bar. And h1 bar is a idempotent matrix and rank of h1 bar is n minus p. So trace of h1 bar equal to n minus p. Therefore, this equal to 2p minus n sigma square plus expectation y curl prime h1 bar y curl. Since this gamma p depends on beta curl and sigma square, both are unknown. So we cannot use gamma p in practice. Therefore, we replace beta curl by their estimators beta curl hat and sigma square by their estimator sigma hat square. Then gamma p hat equal to sigma hat square 2p minus n plus y curl prime h1 bar y curl. This is nothing but a sum of square due to residual based on subset model. That is the model which consider only p explanatory variables. Therefore, gamma p hat square is sigma hat square 2p minus n plus ss residual p. Now we define Mallows Cp as gamma p hat as gamma p hat by sigma hat square is 2p minus n ss residual by sigma hat square. Note, when different subset models are considered, then the models with smallest Cp are considered to be better than those models with higher Cp. Note, if subset model has negligible bias, then expectation due to residual, sum of square due to residual, which we already proved for subset model, expectation due to the sum of square due to residual always bias estimator of sigma square, even if x1 and x2 are orthogonal. So if the subset model has negligible bias, then expectation of SS due to residual should be n minus p sigma square. Therefore, under this condition, expectation of Cp, given that bias is 0, then therefore from this condition we conclude that those points which have smaller bias give a good model. So now if we draw a graph where horizontal axis is P and vertical axis is Cp. If there is no bias, then Cp should be equal to P, then this line passing through origin. Therefore, that means if Cp equal to P, then all points fall on the line, and those points which have smaller bias will be near to the line and those points with significant bias will lie above the line. So this has little bias, and this point are substantial bias. We denote this point as A, this is C, this is C, and this is B. Now we see that point C is above the point A, and it represents a model with lower total error. It may be preferred to accept some bias in the regression equation to reduce the average prediction error. So, in case the full model contains non-significant explanatory variable with zero regression coefficient, then the same unbiased estimator, then the same unbiased estimator of sigma square will overestimate sigma square and then Cp will have smaller value. Therefore, working with Cp depends on good choice of estimator of sigma square. So we will continue with another method in our next class.